a number of problems, methods of doing it, changing the environment. You can, for instance, exploit anisotropic thermal expansion. You could change the crystallization conditions, for instance, for proteins, or I guess you could also use pressure, which would induce changes in the lattice parameters. But I'm not talking about those, I'm talking about exploiting the preferred orientation. And that's, in a way, recovering the third dimension, which we normally use by doing a powder pattern measurement. So in my introduction, I'm going to talk about how to measure it, how we do measure the texture, how we describe it. This is a bit a repetition of what Bob said. Then I talk about the reflection method. You can measure it in reflection, and I have an example where we employed that. And then you can, of course, measure it also in transmission using an area detector or a linear detector. So there are other possibilities to use the texture, and then I conclude. So you have seen that if you have a small single crystal, you get a X-ray diffraction pattern, a single crystal, and if you have one with a second orientation, of course, you get the second orientation of the reciprocal lattice. If you have many crystals, you get these rings, which we are used to. And if you overlay the single crystal pattern, you have the well-known overlap problems. These four reflections all are under the same ring. And it doesn't matter in which direction or in which orientation I have the sample, I will always get the same result. When I have aligned crystals, my reciprocal lattice points are concentrated in one area. It doesn't matter if I have a lot of crystals, if they are aligned, I have not a complete ring anymore. And if I look again at the overlay, the reciprocal lattice, I see that the four reflections are now separated, some degree at least. And if I measure in this direction, I get some kind of powder pattern. If I rotate my sample, I get another powder pattern. If I rotate it again, I get yet a different pattern. That's how we can analyze the texture pattern. So traditionally, one did, let's say, Bragg-Brentano geometry, so that is the reflection method. You have a sample, and you have your focus beam on this sample, and you have your focus in circle, and you rotate the sample in theta to measure it. Of course, you can also rotate it along phi within the disk, and for a texture measurement, you also rotate, you tilt it in the other direction. The problem with Bragg-Brentano geometry is if you do a tilt, you have a displacement error. You tilt your sample out of the focusing circle. So what you get is broad peaks. The solution to that is replacing the X-ray tube by a parallel beam, by a synchrotron. And then you don't have any problem with sample displacement, and you can easily measure tilted samples. That's just something not available for the older crystallographers. So you measure in both directions in 5-degree steps. 5-degree steps because that's what the programs used to analyze texture were written for. They only accepted 5-degree steps, and that's what you get. You get in a polar plot of your orientations along chi and along chi and phi rotation. So this reflection or this orientation, this dot would correspond to an orientation for 35 phi and sky in 50 degrees. If you do that, you measure 1152 patterns. And in each dot, you measure all reflections in the pattern at this orientation. So we get a lot of data. So that's what we can do in a texture measurement. Now we look at it from the point of view of the crystal. If we have a crystal which is sort of non-isomorphic, and we have it in a sample, and we somehow induce orientation, we get a texture like that. And we assume, let's say we have crystals lying, most of the crystal will lie like that, some will lie like that, and a few percent would have some different orientation. If I now just look at the two major orientation, and let's say look at the phase or the reflection from phase 100, I will get a measurement. If I plot each intensity at each orientation in a plot like that, I get this pole figure, which Bob already explained. So this intensity there will come from the orientation of the crystal with the only 30%, and this orientation will come for the other crystal. So we have different intensities for in your pole figure. And if I do it for the other one, or 1O reflection, we get a similar orientation at a different 2 theta value, of course, but now we have the intensity reversed. And for the last phase, we get a pole figure like that. So this plot is at first will be just the intensity measured at each orientation, but then the pole figure will be normalized so that the average is 1. So I can add all this information together and calculate what is called the orientation distribution function, the function which describes the volume flexion looking in a particular direction. And if I have this orientation distribution function, this will describe the whole sample, the orientation of the whole sample. So I can, from the ODF, calculate the pole figure for all other reflections. If I do a measurement in reflection, you know we have this footprint from the X-ray beam on the sample, and that's the danger that we overshoot here. If I'm tilting the sample, my footprint will change, and the more I tilt, the more it changes, and the more it will overshoot. At first, it will still be on the sample here, but it starts, the higher my tilt is, the more I'm overshooting the sample. So I'm not measuring the right thing. I have to do a correction. So if you plot the intensity measured as a function of tilt angle at very small 2 theta, it is a rapid fall off of your measured intensity. So in order to get correct intensities, we will have to do a tilt correction of the measured intensity. And the effect of this is quite severe. If I have this pole figure from this particular reflection, with no tilt correction, I will get something like that. If I do a tilt correction, it will look quite different. So this is important that one does this tilt correction in reflection mode. So, question, can I do deconvolution of the overlapping peak? Does it work? Well, we use the sample as a way to prove the principle of zeolite UTD1. It is a fairly complex zeolite, has a relatively large unit cell. We collected all these 1100 powder patterns, selected 7 non-overlapping peaks, from which we calculated the ODF, and then we measured 5 full patterns to extract, to deconvolute the overlapping reflection using the texture measurement. And that's the solution we got. It's a nice zeolite with a template in it. It's a template in the channel, looks like that. And the structure solution was done by direct method. After deconvoluting the intensity, we have sort of quasi-single crystal reflection. So we could use the direct method, and all the 16 silicon atoms and about half of the oxygens of the framework could be found in the best EMAP. And the rest was then located using difference Fourier. And the Rietveld refinement actually had to be done in the asymmetric space group, and so there were actually 32 silicons in the asymmetric unit, and so about 350 parameters for the refinement. So I already pointed out that there are problems with the reflection mode. We have to do this. We have to use a relatively large sample, which has to be homogeneous. Now, if you get that from a rolled steel or from a geological sample, that's no problem. But if we have to prepare it ourselves from a powder sample, that is not so easy. It has to be homogeneous because the footprint is not constant in the diffraction experiment. The data analysis of the data is difficult because we have this very large correction for the tilt. And synchrotron beam time, you have to do the correction, you have to do 1100 measurements, you have to do 5 complete measurements, so that all takes time. And it will take about 3 days on a synchrotron to measure this pattern. Now you can do that to prove the principle, but you cannot do that on a regular basis. So there we had to find alternatives, and of course, one way is to use an area detector. So if you use an area detector, you have your sample, your beam, and your area detector, and you measure your tilt in one shot. So you don't have to do the tilts, or something similar to the tilt. It's not exactly the same measurement, of course. And you only have to rotate it around one axis to get all the orientations. And again, we do it in 5-degree steps, this orientation. You have the analysis of the area detector image. We cut out 5 degrees pies or sectors, and you do that all around the image, and you have 70 sectors, 72 sectors, and you get 72 diffraction pattern at the same time. So again, then you do another frame with a different psi orientation, and you get again 1200. There are now more patterns, because in the reflection mode you cannot tilt by 290 degrees. And the advantage here is you have very good statistics in very short time. So I haven't said how we measure the diffraction, how we prepare the texture pattern. Of course, if you have it from a steel or from a geological sample, you don't have to do that. But we want to analyze powder samples and want to deconvolute the powder pattern, so we have to prepare it. There are several ways of doing that. We have tried many things. Of course, in certain cases, you can use magnetic alignment or in alignment in electric field, but normally that is not the case. The best one method which seemed to work for us was the following. We mix a sample in a polymer dissolved in a solvent. Polystyrene is ideal because it doesn't crystallize, so we don't have any diffraction spots coming from the polystyrene. Then you let the solvent evaporate till we have a sort of a viscous mixture, and then put it in the groove of some dye which we made like that. So we put it in here, your sample, and then pressed it with another one here to make a film out of the polymer mixture. Originally, we thought we had to do very high pressure, so it's a very robust cell. It turns out it's not necessary to have really such a high pressure. But then you press it, open it again, remove the film, fold the film, and repeat the same thing several times till your solvent has evaporated and you can't press it anymore. That seems to work quite well. I will show pictures of the achieved preferred orientation. So the area detector, the pros of the area detector are the samples can be very small. You can make it just like I described, and they are fairly easy to prepare. The data collection can be done in a few hours on a MAR image plate. There are no tilt corrections required, and we get good counting statistics. The disadvantage are we get relative broad peaks, and because of the limited size of the detector, we have a restricted to the theta range. Of course, you can put your detector further away, and your peaks are less. We have a better resolution, but the resolution is ultimately limited by the pixel size of your detector. And when you go out, of course, you reduce your to theta range again. So we were looking for alternatives, and luckily in the SLS we built this beautiful instrument with a linear detector. This one has 120 degrees range. It has a, oops, no, it's the same thing. You have a Eulerian cradle, and you can place, I point this out, your 120 degrees symmetrical to the beam. Of course, if you have a linear detector, you have to do more rotations again. So, but the setup is like that. You have the detector, your sample, and you have your beam. You have to rotate in this direction and perpendicular to do. We have to do 2 rotations again. So we want to, if possible, reduce the number of orientations we have to do, and that can be done, because if you look at the original setup where we had a very dense population of orientation in the center, and so it's not an equal density, not an equal distribution of the measured orientations. This was a requirement because the programs couldn't deal with other distribution of the orientation. But in the MOUT program, which we are now using, you can have an optimized coverage, and you can get away with only 300 measurements. So that shortens, of course, the data collection time, and because the measurement time is quite quick on the Meitner detector, it can do measurement very quickly. I said that we have the detector in a symmetrical position, so we measure at the same time in the plus direction and in the minus direction. And because we are looking from different orientations, we get different patterns. The pattern in the plus direction looks different from the minus direction. And that's true for every measurement. So this one could actually be used in a normal measurement to check whether you have preferred orientation or not. The fact that we have two measurements at the same time means we have more orientation method at the same time. The effect is not very different for low angle reflections at 1 degree. So the red part is the plus direction, say, and the black dot is for the minus direction. For high angle, it's quite different, so we really have additional measurements at the same time. So one thing I have to point out in this measurement, we get the same problem, a missing cone in the center of if we plot it in the correct pole figure way, we see that we have a missing cone in the center just for as it becomes bigger as with higher 2-theta angle. But there are a lot of advantages with the transmission mode. We have high resolution. We have a large angular range. We have very fast measurements. We can measure in 2 to 10 seconds per pattern. So we can measure 300 patterns in about 10 to 15 minutes. The sample statistic is very good. And because we have this 120-degree detector, we can measure 2 patterns at the same time. And the staff at the SLS was very helpful, so they made it possible to oscillate the sample around the position, so we have an integration plus minus a few degrees at every position of the detector, of the sample. So the advantage of the SLS is also that we have very helpful beamline staffs there. So the test example for this setup, showing with zirconium phosphate here, and you can see the patterns the pattern look very sharp, quite well resolved, quite high, good statistics. So you can do something with that. What is the analysis procedure? So first you have, of course, to prepare your sample using forces, shear forces, with differently spelled. You can then do a fast measurement with optimized coverage. We determine the texture using non-overlapping reflection, non-overlapping low-angle reflections with program mode. Then we analyze the texture to select the most useful sample orientations, and then we deconvolute the overlapping reflection and solve the structure by direct methods. To show you how well the texture can be measured and described, this is observed pole figures from this sample here, measured with the linear detector here, and you see very good texture we could obtain. And if you calculate then the ODF, you can calculate back the texture, and that's a comparison between the measured texture and the calculated calculated pole figures. So the agreement is very good. Now, if we want to deconvolute overlapping reflections, we have to calculate, as I said, the pole figures. That's, for instance, for these two reflections which are overlapping. But if we now look here, there is no information. So we have to find the most useful orientation to deconvolute these two peaks. And of course, the best orientation is where the difference between these two pole figures is the largest. So if you subtract this pole figure from this, you get this difference. And of course you get some negatives, but with the negative, we cannot deal with negative values in pole figures, so we do the opposite as well, subtract this one from this one, and we get this. So the most useful orientation for doing the deconvolution would be measuring here and here, and of course also these two positions. So what we do, for each overlapping reflection, we do the differences between all of the overlapping peaks and find out which are the optimum positions to measure and to analyze the texture. And by that we can reduce the number of orientations we have to use to do the texture, to do the deconvolution of the overlapping peaks. So how many of these different orientations do we really need? We did an analysis, so that is the R value of the deconvoluted intensity or structure factor compared to the calculated structure factor. The untextured sample, if you do that, the conventional Lebye extraction, of course, the non-overlapping reflections are fairly good. When the overlapped reflection get an R value because of the equipartitioning, get a very high R value. If we use now 8 textured patterns for the analysis, for the deconvolution, the R value drops, and it doesn't really improve if you use more patterns. So we can work with a limited number of carefully selected orientations. You can combine this one, which is high resolution but not as high, as you get a measurement from an untextured sample on an instrument with an analyzer crystal. It will improve a little bit. But the result here is, if you do a careful analysis of your most useful orientations, you can get away with a limited number of carefully measured powder patterns. To compare that in another way, this is the equipartition data plot here with fcalc and the one which we have extracted from the Lebye extraction from the powder pattern. You get the distribution. Ideally, it should be on the diagonal. We get the distribution something like that. So you see how many reflections are wrongly measured or wrongly estimated. And after the textured data, the agreement between the measured data and the observed, the calculated data is much better. So, other benefits from textured data. If you look at these pole figures here, if you're an old crystallographer or mineralogist, it will remind you of the pole figures the mineralogists used to draw when they measured crystals with the two-circle goniometers. They would plot the angles measured from a crystal on a stereographic projection and then find out what the symmetry is of the crystal. Now this one is a series of pole figures we measured on a sample we couldn't index. It seems to have a very large lattice parameters and not too well crystallized, so we couldn't index it. But you can see that here and this one seems to be single poles, so that could correspond to axis of the crystal. Now it's sort of random oriented, so we will orient this, move this to see it better. We will move this peak into the center. And of course, we have to do that for all the other pole figures as well. And it becomes already more symmetrical. So this one is then could be oriented like that. So we do that as well, and for all the other ones. And now we can easily see that there is symmetry in our pole figures. Unfortunately, what we see is the sample symmetry, because by orienting our crystals, we induce symmetry MM2. So that's what we see here. And the crystal itself are actually triclinic. That you can see not very easily, but this one is not 90 degrees from this position here. Yeah? So careful analysis shows that it is really triclinic. But in order to do that, to do an analysis like the old crystallographer did, you need an old crystallographer to do that, to transfer these observations, these positions of the faces onto a stereographic projection. So we can do indexing like the old crystallographer did, but you need an old crystallographer to do that. The maxima in the pole figures give us the direction of the lattice planes, as we have from optical analysis of a crystal. And here we have the old crystallographer. He has then put all the data on this Wolf's net, and we get something like that. And if you remember, I don't know how many of you understand these pole figures. We have great circles here on which belong to a zone. And so there's a peak here, there's a reflection here, and there's a reflection here. That's easy on one zone, so we know they belong to a same zone. And of course, we also know that D values we can measure, that old crystallographers couldn't do that, gives the length of the reciprocal vector. So we actually can construct the reciprocal lattice. And that's what this crystallographer did. We took the angle for a reflection and the length, plotted it on a piece of paper, and then you can find out what the reciprocal lattice is, and you can index these reflections as shown here. So you can do some old crystallography, and Lynn is going to talk about old ideas. This is an old idea with new opportunities, indexing a crystal on using texture analysis. Oops. So my conclusions are, it is now possible to do a texture measurement almost as routinely as a normal powder data collection. Giving a texture sample, good texture data can be obtained within minutes on a modern synchrotron. And with this data, we can overcome the overlap problem to a large extent, and we can obtain single crystal-like data. And pole figures can then be determined, and space group and indexing the powder. Pole figures help to determine the space group and indexing the powder pattern. just what I showed. And therefore, texture management is a viable alternative if more conventional approach to structure solution fails. And something Bob already mentioned, don't be afraid of texture, use it. You have tools to deal with it, and you can get additional information from it. Thank you for your attention.
Okay, we have time for questions. Yo.
I have a question about the footprint issue.
Oh,
yeah, sorry. About footprint issue, at least in the reflection geometry, is it not really you speak about the gauge volume because of actually you should take into account the diffracting volume, not really a footprint. I mean the reflection geometry, of course, and transmission is more or less the same.
I'm not sure I understood acoustically. But you're asking about the volume something.
Okay, my question is about the footprint issue. In case of reflection geometry, is it not considered the gauge volume, which is diffracting volume, rather than footprint issue?
Yeah, well, yes, that's true. I just showed it, that's what you can see. But it's your volume, what you actually then measure if you do the correction measurement to do the correction. You measure it, you don't calculate it, we measure it because the volume depends then on the absorption coefficient.
There must be more questions. Yes, John.
So in the optimized pole figure coverage, you had 300 random looking points.
Yeah.
How do you come up with these points and decide which points to measure?
They are separated by, well, in this, you can do different optimization, but this one is 15 degrees between the orientations. Is that right?
Well, I think that one was probably done just sorting, the angle. So it's actually depending on the instrument. So you are just taking the angle in a so-called equal area space on the pole figure. Okay, but then you have to, in the plot it seems like random because with the new instrument, you don't measure really the point where they are. Depending on the HKL has, on the 2 theta, as Christian was showing, you have something turned, okay? So you cannot really select exactly the point on the hexagonal grid that cover the equal partitioning, okay? So you end up taking the closest point to each. And so the closest point actually turned out to be a little bit random, but it's only because it's the closest point to an hexagonal grid over the pole figure.
So the list of angles that you would, if you sit down in front of the diffractometer and you want to do the experiment, where do you get the list of angles? Is that distributed with Maud? How would I know which angles to type in to the diffractometer?
Yeah, that we obtained from Maud, yeah.
Yes.
It's Paul from Sheffield. I was just wondering, with regards to the kind of morphologies of crystals that you can do texture analysis on, how non-isomorphic do you need your crystals to be to get texture?
How big the crystals have to be?
How non-isomorphic?
How non-isomorphic? We never did a measurement, but it's as Bob Frandril said, even if a cubic crystal, you get some alignment as well. Yeah, but of course, if you to get this nice separation of or orientation of the crystals, it's nice to have needles or platelets. Yeah. Yes, they have to be. That's the limitation. To some degrees, I mean, the more more non-isomorphic the crystals are, the better the method will work.
Any further questions? If not, then join with me in thanking Christian once
thank you.
again for a presentation. I'm not sure what Bill was going to say. Yes,